And the guy who's being surveilled need only configure the computer on the other end to accept packets with bad checksums, and he can send all of his communications with bad checksums, and he'll be completely invisible to your surveillance. So that's a difficult problem, there's a lot of other research out there that discusses it. The other thing that you need to be concerned with is unauthorized use of the wiretapping system you're building, and that's really what this talk is about. You need to prevent people who don't have permission from provisioning wiretaps, and you also need to make sure that those who do have permission are only collecting the information that they're authorized to collect. That second thing, there's a technical term for it, which is minimization. And those two things are really the subject of this talk, and I want to make sure that's clear because the last time I gave this, some people didn't understand that. This talk is about gaining unauthorized access. This is Blackhat. So this is a network map to try to give you more of a real-world picture of how this is going to look. This is an ISP network. There's an edge router down here that's providing service to a bunch of customers. It's an intercept access point. And then there's the service provider management network that hopefully is firewalled off from the rest of the ISP's network. And in it, you've got a bunch of computers, including an SNMP management host and a mediation device that you're using to operate the surveillance system. So this is how things are supposed to work. The mediation device would send this SNMP v3 interception request through the network to the edge router and provision a wiretap. And then the wiretap would flow back across that red link there from the router to the mediation device, which would collect it and send it off to the law enforcement agency. This is an idealistic attack scenario. Some guy out on the internet sends an interception request to that same router, provisions a wiretap, and has the results of that wiretap sent back to his machine, again, out on the internet. So how do we do that? What we're going to need to do is send an unauthorized interception request. It's a single, properly authenticated SNMP v3 packet, which accesses this tap MIB, which, as I told you before, is available online. You need to know the correct username and password for the interface. You also have to know the SNMP v3 engine ID, engine boots, and engine time values. Those values are designed to prevent replay of SNMP v3 transactions, and they are readily available from the router if you're allowed to transact SNMP with it. So it will tell anyone what those values are because they're not supposed to be secret, and you can share them between hosts. So if you know them, you can tell someone else and they can use them. The attacker would also need to be able to, the attacker would need to be able to send a packet the interface will receive. So packet filtering could impact this, but again, it's a single UDP packet, so you could spoof it. And I'm going to talk a little bit about that. And encryption might prove to be an obstacle, but only if they did it right, and they probably didn't. So I'm going to talk about that too. Let's start with the beginning. Let's talk about this correct username and password business. It actually turns out that you don't need the correct, or for unpatched routers, you didn't need the correct password because of a vulnerability in the SNMP v3 implementation that this actually affected a whole bunch of different vendors, and not just Cisco, but it was disclosed in the summer of 2008. So the way that SNMP v3 messages are authenticated with this message digest, and so you, as the client, you calculate the digest, you attach it to the packet, you send the packet to the server. What the server is supposed to do is to see how long the message digest you sent was. And if it's not 12 bytes long, it's supposed to throw the packet out. It pretty much says that in black and white in the RFC. But a bunch of people didn't implement that step. And so they set the packet onto so the next thing they do is the server does is calculate its own HMAC for the packet. And then it wants to compare its HMAC with the HMAC that you sent. And a lot of these comparison operations were implemented as shown. They take the packet's HMAC buffer and their HMAC buffer, and they compare using the length of data that was in the packet. So the consequence of that is that if you send a single byte, as long as that one byte is the same as the first byte of the valid HMAC for the packet, your packet is accepted as valid. And so really what you do is you send 256 of these things, one for each possible byte, and one of them will be accepted. Or the other way you can do this, and it gets more complicated, is that the valid HMAC changes constantly because of the engine time. So you can actually send the same byte over and over and over again, and one of your packets will be accepted. So as I said, this was disclosed in June 2008. I hope everyone has patched this, but people tend to be slow about patching routers. So you've got to take the router down. The new version of iOS might have a bunch of new software features that you want to test on your network, and so it can be complicated to deal with this. So I hope that everyone is patched by now, but there might still be routers out there that aren't patched. What's also interesting is that most of the versions of iOS that support this lawful intercept technology were not vulnerable to this particular vulnerability. And given that this vulnerability existed in implementations for like 6 years, it's surprising to me. There must have been 2 different SNMP implementations floating around in their code bases, and one of them didn't happen to have this flaw. But I did find a specific version. There may be more, but I did find a specific version in the list of vulnerable versions that happens to also support lawful intercept, and it runs on the Cisco 10000 series edge routers. These routers are for cable modem companies or DSL companies that are serving like large numbers of customers. These things are out there on the internet, and potentially there's a lot of consumer data that's flowing through them. So let's say you're trying to break into this lawful intercept system, and these guys have patched the router. So that vulnerability is not available anymore. You're going to need to actually have the valid username and password in order to get in. You're going to have to brute force them. Turns out SNMP v3 makes that really easy for you, but through a very classic mistake. They have very verbose error messages. If you send a packet to an SNMP v3 interface and you have the wrong username, it will tell you that the username was wrong. If you have the wrong password, it will tell you that the password was wrong. And so it's easy to guess usernames until you get one that's accepted, and then you guess passwords until you get one that was accepted. And that helps break up the amount of entropy that you need to guess without getting any feedback. All kinds of different systems have been implemented this way in the past, and usually this ends up getting disclosed as a vulnerability with a very low CVSS score, and they fix it. But it's actually going to be hard to fix SNMP, and I'm going to talk about that a little bit later. So let's say you've brute forced the username and password. You might be a little bit concerned, because it's going to take you a while to try all those guesses, that you might be noticed doing that, right? All that traffic that you're generating, you would think that might be picked up by the people operating the network. But unfortunately, there really isn't much of an audit trail in place that would alert the network managers to this activity. So I originally thought that this was an implementation flaw. In SNMP v2, if you send a message so they didn't have usernames and passwords in SNMP v2, they had community strings, which was sort of like a password. But if you sent an SNMP v2 message to a router that was configured to do traps, and you had a bad community string, it would do this authentication failure trap to the SNMP management server. So the network managers would know that somebody's screwing around. Somebody is sending us messages that are not properly authenticated. And all the documentation seemed to strongly suggest that if you configured SNMP v3 with either notification traps or informs, is what they're called in v3, that they would be generated if a bad username and password were sent. But it turns out that doesn't actually happen in practice. I tested this on a bunch of different iOSs, and no traps or informs were generated when bad passwords or usernames were tried. So I told Cisco this, and they spent some time thinking about it, and they decided that the behavior was as designed and the documentation was wrong. And so they actually have this bulletin in CCO, which you can look up, which explains that the documentation seems to imply that we will generate traps when there's an authentication failure, but in fact we do not, and it's supposed to be that way. So you can try bad usernames and passwords all day long, and no one will probably notice. The other thing is that once you get in, you would think you would be noticed. Once you crack the right username and password, and you actually provision a wiretap, you would think there would be an audit trail that would be generated, and they would know that the wiretapping system was being used. It turns out that you can actually turn the logs off. In the MIB for provisioning a wiretap, the tap MIB, there's this notification enable value, and you can set it to false. And if you set it to false, no traps or informs will be generated denoting that a wiretap took place. This is also as designed, and to me it's bizarre. Most kinds of systems have audit trails built into them and various levels of authorization. So if you're logged into a Unix shell, you're generating all the syslog activity, and you can't turn that off unless you're root. right? DHCP servers have audit trails. SMTP servers have audit trails. Every kind of computer system that we have audits the activity that the users are engaged in. But this is different. In this case, the user can turn the logs off. And it seems that a bunch of different lawful intercept technology that is completely unrelated technically has this same architectural feature. So there was this article in IEEE Spectrum back in July of 2007, which is very interesting, which involved some Ericsson cellular phone switches that were in Greece. And I want to make it clear, no Cisco equipment was involved here. These were totally different machines built by a different company for use in the cellular network with a completely different technical architecture, except that they had this same flaw, that there was a disconnect between the device that performs the wiretapping and the actual device that, or the device that's used to provision the wiretaps. And the logs were all kept on the provisioning device and not on the device where the actual wiretaps occurred. And so what happened is that someone got a rootkit installed on the actual cellular phone switch, and that rootkit accessed this interface for wiretapping, and it could do so without generating any audit trail because the audit trails were all over here on the provisioning device, which it never touched. Ericsson discovered this because there were some problems with the switch. It started crashing, and they sent some escalation engineers down to Greece to find out what was going on, and they started looking through the core dumps, and they actually found assembly code in the core dumps that their company didn't write. It's like the support escalation nightmare of all time, right? You find this assembly code, your company didn't produce it, and it turns out it's spying on people. There's an origin to this architectural flaw, and I don't know exactly what it is. And I'll talk to you about that a little bit later. But there's some reason why all these systems have been designed this way, and I don't know exactly why. But I think it's a problem, and I have a suggestion for an alternate architecture. So there's one other reason why this is a problem, even if you decide that you're not concerned about unauthorized use, and that is that allegations of misuse of the system cannot be investigated. If somebody says, I was wiretapped without authorization, you have no way to go back and see whether or not they're lying. And so that's an interesting problem in and of itself, I think. So you can crack the password, or you can exploit that vulnerability to get in. There's no logs that are being generated of your activity. What about the output stream? You would think that the output stream would only go to the mediation device. And so that would be kind of a problem because you would need to own the mediation device, and it's probably pretty secure. But it turns out that you can send the output stream anywhere that you want. You can send it to any destination address on the global internet over any port using one of 4 different encapsulation methods. A UDP, 2 different UDP formats, one of which is based on RTP, a TCP, and an STCP stream. So it's very unlikely that your output stream is going to be packet filtered or even noticed. And so, for example, you could send all of your wiretap out over port 53 as a bunch of UDP packets. And I put a picture of Dan Kaminsky up here because every time I think about port 53, I think about Dan. So it's very unlikely that your wiretapping contents are going to be discovered flowing across the network, and you can pretty much send them anywhere you want once you've got this packet accepted. So usually people who are configuring routers will use access lists to protect them. That is the primary security feature of iOS. All of the documentation for either both the SNMP v3 authentication vulnerability I mentioned before, as well as the hardening guides, suggest that you create these infrastructure access control lists, where you basically say the service provider LAN is the only place that will accept SNMP